A tipping point that scientists didn't even know about may have just been crossed in Antarctica.
Antarctica is making a final, desperate move, and if it succeeds, coastlines around the world will be erased. Deep in the most remote part of the continent, a single glacier, a slab of ice the size of Great Britain, is breaking apart. A crack stretching tens of miles has been tearing across its surface, a wound in the frozen landscape. But the real danger is not the crack you can see. The real danger is the invisible force eating it away from below. For years, scientists believed it was stable. It was not stable. It never was. Now, its collapse could trigger a sea level rise measured not in inches, but in feet. A catastrophic event that would permanently redraw the map of the world. Before we begin, I want you to subscribe to this channel right now. What we're talking about here isn't just stories, it's the reality we're living in. By subscribing, you help make sure this information stays visible instead of getting buried and forgotten. Now let's get into it. Not a flood, not a storm surge, an erasure. So, an international team of scientists launched one of the most ambitious and urgent expeditions in history. They have raced to the bottom of the world to look a planetary-scale disaster directly in the eye. The real question is, are they there to stop it, or are they just there to document our future? The Thwaites Glacier was supposed to be a constant. It sits in West Antarctica, a region so vast and so cold that for a century it was treated as a fixture of the planet, an eternal block of white on the bottom of the globe. This is not a river of ice. It is a geological feature, a frozen plug holding back an empire of ice behind it. At its widest point, it is 80 miles across. It extends nearly 4,000 feet down to the bedrock below. The sheer volume of water locked within it is difficult to comprehend. If it were to melt entirely, just this one glacier, it would be enough to raise global sea levels by more than 2 feet. To put that in terms that mean something, it is enough to permanently submerge parts of Miami, New Orleans, and New York City. And that is just the beginning. Thwaites is a gateway. It acts as a cork in a very large bottle, holding back the rest of the West Antarctic ice sheet. Its collapse would unplug the drain, accelerating the flow of enough ice to eventually raise seas by 10 feet. This is why some glaciologists do not call it Thwaites. They call it the Doomsday Glacier. For most of modern history, this threat was purely theoretical, a mathematical curiosity. The men who first raced to the South Pole, Scott and Amundsen, saw a landscape of impossible static cold. They fought against wind and ice that seemed timeless, unchanging. Their journals speak of a continent defined by its permanence. But that perception was codified into global policy. The Antarctic Treaty of 1959 designated the entire continent a natural reserve, devoted to peace and science. It was a frozen museum, a laboratory at the end of the Earth, not an active threat. For decades, the scientific community treated it as such. Early satellite monitoring in the 1970s and 80s revealed small changes, minor melts along the Antarctic Peninsula, the continent's most northerly and temperate point. But the great ice sheets of the interior, East and West Antarctica, were believed to be in a state of near-perfect balance. The snow that fell each year roughly equaled the ice that was lost to the sea. It was a system that had found its equilibrium over millennia. Any significant change was thought to be centuries, if not thousands of years, away. The scientific world turned its attention elsewhere, to Greenland, which was melting faster, losing billions of tons of ice every year. Greenland was accessible. It was understood. West Antarctica was the sleeping giant. Too remote, too cold, too difficult to study in any meaningful way. It was a problem for a future generation, and this was the fundamental miscalculation. The giant was not sleeping. It was waking up. The first signs of trouble were subtle, buried in streams of satellite data. Through the 1990s, radar instruments began to map the flow of the ice, and Thwaites was moving faster than it should. Before we go further, take a second to subscribe if you haven't already, because the more people who see this, the harder it becomes to ignore what's really happening. All right, let's continue. Not by much, just a few percent, but it was enough to make the handful of scientists watching it very, very nervous. Then came the cracks. By the 2010s, the satellite imagery revealed a rapidly growing chasm spreading across the glacier's floating ice shelf, the portion that extends out over the ocean. This was not a small fissure. It was a continent-scale fracture, growing at a rate of miles per year. The glacier was tearing itself apart. But why? Glaciers typically die in one of two ways. They can melt from the surface as warm air turns snow and ice into runoff, or they can calve at their edge as icebergs break off into the sea. Thwaites was doing both, but it was also doing something else, something far more dangerous. It was melting from the bottom up. The true source of its destruction was not the air above it, but the ocean beneath it. And to understand what that means, you have to understand the single most important part of any glacier like this one. It's called the grounding line. The grounding line is the precise point where a glacier loses contact with the land and begins to float on the sea. It is the fulcrum of its stability. Think of it as the ankle of the entire ice sheet. As long as the glacier is firmly anchored to the bedrock, it remains relatively stable, its flow regulated by friction. But if that anchor point begins to move, the system starts to break down. And the grounding line of Thwaites Glacier has been retreating, rapidly. For decades, a current of relatively warm, salty water known as circumpolar deep water has been circulating around the Antarctic continent. Historically, a natural barrier of colder coastal water kept this current offshore, away from the great ice shelves. Climate change has weakened that barrier. The circumpolar deep water is now pushing onto the continental shelf and flowing directly underneath the Thwaites ice shelf, reaching the one place it can do the most damage, the grounding line. This water is only a few degrees above freezing, but to an ice sheet that has existed in a state of deep cold for thousands of years, a few degrees is a blowtorch. It is melting the base of the glacier, unpinning it from the bedrock. It is not a gentle, even melt. It carves vast cavities and channels into the underside of the ice, some of them hundreds of feet high, creating cavern systems larger than the island of Manhattan. These hidden channels don't just melt the ice, they lubricate it. With less friction to hold it back, the glacier's forward motion accelerates, stretching the ice and worsening the cracks on the surface. The glacier is not just being attacked, it is being hollowed out from within, its very foundation dissolving into the sea. And until recently, no one had ever seen it happening. The scale of the threat demanded a response of equal scale. In 2018, the United States and the United Kingdom launched the International Thwaites Glacier Collaboration, or the ITGC. It is the largest and most expensive joint research project ever mounted in Antarctica. Not a small scientific mission. It was a mobilization, a 5-year, multi-team effort to throw every piece of advanced technology humanity possessed at a single block of ice. The logistics were a nightmare. To get to Thwaites, you have to cross the most treacherous seas on the planet and then traverse hundreds of miles of unstable ice. The working season is brutally short, and limited to a few brief months of Antarctic summer when temperatures are merely unbearable, not unsurvivable. Teams of scientists, engineers, and support staff established deep field camps on the ice itself, small islands of humanity in a wilderness of white. Their mission was to map the glacier from top to bottom. From the sky, aircraft equipped with ice-penetrating radar flew thousands of precise flight lines, creating a three-dimensional map of the ice thickness and the shape of the bedrock below. On the surface, teams drilled through half a mile of solid ice to deploy sensors, stringing out seismic arrays and GPS stations to feel the glacier's pulse, its daily movements, its deep, resonant shudders. But the most critical part of the mission involved going where no one had ever gone before, underneath the ice. One team used a hot water drill, a massive, power-intensive machine that can take days to melt a narrow borehole through 2,500 feet of ice. The moment the drill breaks through into the ocean cavity below is one of extreme tension. They have a limited window of a few hours before the hole refreezes itself shut. In that window, they lowered a torpedo-shaped robotic submersible called Icefin. It is an autonomous vehicle packed with cameras, sonar, and oceanographic sensors designed to be their eyes in the dark. The first images that came back were staggering. The scientists were not just looking at a featureless ice wall, they were flying the robot through a landscape of strange, terraced slopes and scalloped crevasses, formations sculpted by the relentless melt. And they confirmed their worst fears. The water at the grounding line was warmer than any model had predicted. The rate of melt was higher than they had thought possible. Another team took a different approach. They deployed a larger, long-range autonomous submarine named Bodie McBoatface by a public pole. Launched from an icebreaker ship at the edge of the ice shelf, the submarine was sent on a perilous multi-day journey into the darkness beneath the floating glacier. It traveled for hundreds of miles under a ceiling of ice half a mile thick, mapping the seafloor and the shape of the ice cavity with unprecedented detail. It was a mission with no possibility of rescue. If the submarine became trapped or lost communication, it would be gone forever. It found deep channels carved into the seabed, that had pathways that were allowing that warm circumpolar deep water to penetrate dozens of miles farther inland than previously believed, attacking the grounding line from multiple directions. The science had confirmed it. This was not a simple, linear retreat. It was a complex, multi-pronged assault. The ITGC was not just measuring a glacier, it was performing an autopsy on a living patient, and the diagnosis was terminal. The glacier was dying, and it was dying faster than anyone had dared to imagine. The new data from the ITGC allowed scientists to build better models, more accurate forecasts of the future. The numbers that came out of those models are not comfortable. The first stage of the collapse is the disintegration of the Thwaites ice shelf, the floating section that acts as a buttress bracing the inland glacier. With warm water eating it from below and massive cracks tearing it apart from above, the shelf is becoming dangerously weak. Scientists now believe it is entering its final phase. Its collapse will not be a slow melt over decades. It will be a rapid, violent shattering, an event that could unfold in a matter of months or even weeks. We have seen this before. In 2002, the Larsen B ice shelf, a structure that had been stable for 12,000 years, disintegrated completely in just 35 days. The satellites watched as it shattered like a pane of glass. When the Thwaites ice shelf goes, the cork comes out of the bottle. The inland glacier, now unbraced, will accelerate dramatically. Its flow rate could double or even triple, dumping hundreds of billions of tons of ice into the ocean every single year. This alone will drive significant sea level rise. But that is not the doomsday scenario. The doomsday scenario is what happens next. Thwaites is a gateway glacier because of the land it sits on. The bedrock beneath most of the West Antarctic ice sheet lies below sea level, in a deep basin. And crucially, it slopes downward as you go farther inland. This creates a terrifying feedback loop, a process known as marine ice sheet instability. Once the grounding line of a glacier like Thwaites retreats past a certain point onto that downward slope, it can become unstoppable. As it retreats into deeper water, the height of the ice cliff at the ocean's edge gets taller. A taller cliff means more ice is pushing from behind, which speeds up the flow. And a faster flow stretches and thins the ice, which in turn allows the grounding line to retreat even faster. It is a runaway process, one that once started may not be able to be stopped by any force on Earth. This is the mechanism that could unlock the entire West Antarctic ice sheet, setting in motion the full 10 feet of potential sea level rise. Not a flood that comes and goes, a permanent change, a new higher coastline for the entire planet. 10 feet is a number so large it feels abstract. It is not abstract. 10 feet of sea level rise means the end of South Florida. The entire region, from Miami to Palm Beach, would be underwater. The homes of 6 million people, gone. It means the effective erasure of New Orleans, much of Houston, and vast swaths of the eastern seaboard from North Carolina to Boston. In Europe, it means the loss of Amsterdam and Rotterdam, and the inundation of Venice, the transformation of London into a coastal city under permanent siege. In Asia, the consequences are even more catastrophic. Low-lying megacities like Shanghai, Dhaka, Bangkok, and Ho Chi Minh City would be rendered uninhabitable. Crucial agricultural lands like the Mekong and Nile deltas, which feed hundreds of millions of people, would be poisoned by saltwater and lost forever. The displacement would be unimaginable. An estimated 600 million people live on coastlines that would be threatened by this level of rise. It would trigger the largest migration in human history, an exodus away from the coasts with crippling economic and political consequences. The world's financial centers, its ports, its military bases, a huge percentage of our most critical infrastructure sits right at sea level. This is not a distant environmental problem. It is a direct threat to the stability of modern civilization. And the key to when this happens lies locked in the ice of a single glacier. The most unnerving discovery to come out of the recent research is not about the glacier itself, but about the very physics of how ice breaks. For years, models of ice sheet collapse were based on relatively straightforward physics. But some scientists now believe these models are missing a critical and much faster process. They call it marine ice cliff instability, or MICI. The theory is simple and terrifying. Ice can only support its own weight up to a certain height. Once an ice cliff that terminates in the ocean gets taller than about 300 feet, the stresses at its face can become so great that it will begin to collapse under its own weight. Or it is a purely mechanical failure, not a slow melt, but a structural collapse. The front of the glacier would simply start to crumble, calving off massive sections in a rapid runaway chain reaction. If the MICI hypothesis is correct, it means the collapse of Thwaites could happen much faster than even the worst-case conventional models suggest. It would not be a process of centuries. It could be a process of decades. The entire scientific effort at Thwaites is now a race to answer one question. Is MICI real, And is Thwaites vulnerable to it? The data is ambiguous. Some evidence suggests the molecular structure of the glacier's ice is strong enough to resist this kind of rapid failure. Other evidence from ancient submerged coastlines suggests that in the Earth's past, sea levels have indeed risen in sudden, rapid pulses. Exactly as the MICI theory would predict. We are living in an unprecedented experiment, and we don't know the rules. We are pushing the climate system into a state it has not been in for millions of years, and we are discovering that the planet's ice sheets have mechanisms of collapse we are only just beginning to understand. The scientists drilling into the ice, the robots exploring the dark water, the satellites watching from orbit, they are not looking for a solution. There is no engineering solution to this problem. You cannot build a wall to hold back a continent of ice. You cannot pump the warm water out of the Amundsen Sea. The work being done at Thwaites is not about prevention. It is about prediction. The central question has become one of timing. Is this a crisis for our grandchildren, or is it a crisis for us? Does a city like New York have 100 years to prepare, or does it have 30? The answer to that question changes everything. The International Thwaites Glacier collaboration has fundamentally rewritten our understanding of Antarctica. It has transformed the continent from a static, frozen museum into a place of violent, rapid change. The sleeping giant is awake, and we now know it is capable of moving far faster than we ever believed possible. The project has proven that the grounding line is in chaotic retreat, that warm ocean water is the primary culprit, and that the glacier's main ice shelf is fractured and failing. It has delivered a wealth of data that has made our climate models better, and our predictions sharper, and our future more frighteningly clear. But it has also revealed the limits of our knowledge. But despite the immense effort, the exact timeline of collapse remains profoundly uncertain. The physics of ice fracture on this scale are still on the cutting edge of science. The system is too complex, too vast, and too sensitive to small changes for any model to provide a single, certain answer. The science has defined the cliff edge. It just cannot tell us the exact moment we will go over it. The fate of Thwaites is no longer an academic debate. It is a geopolitical reality. The glacier itself is located in a part of Antarctica that is unclaimed by any nation, a true global commons. But its collapse will be felt by every nation with a coastline. The water that is currently locked in its ice will not stay in the Southern Ocean. It will redistribute across the globe, raising the sea everywhere. The problem has a single source, but its consequences are universal. And yet, there is no global authority with the power to address it. No international body capable of managing the retreat of hundreds of millions of people from the world's coasts. The science has given us a clear and urgent warning, but our political and economic systems are not built to respond to a threat of this nature. A threat that is slow-moving until it is suddenly very, very fast. A threat whose worst effects may be decades away, but whose trigger point may be happening right now. Thwaites Glacier is not a cautionary tale, not anymore. It is a live broadcast. We are watching in real time as one of the planet's great stabilizing features begins to break down. The cracks on its surface are not just fractures in the ice, they are fractures in our assumption of a stable world. The work of the scientists on the ice is heroic. They are enduring some of the harshest conditions on Earth to give us the one thing we need most: time. Time to understand, time to prepare, time to adapt. The data they have gathered is a gift, a final warning from the bottom of the world. But it is not a solution. The glacier is moving. The ocean is warming. The grounding line is retreating. The vast, silent continent is stirring, and the clock that is ticking beneath its ice is measuring more than just the flow of a glacier. It is measuring the remaining lifespan of the world we thought we knew. The engineering has given us a window into the disaster, but it cannot stop it. And somewhere in the dark, cold water beneath the ice, the final act has already begun.